Hello everyone. Today I'm going to talk about image matching with least square method. The outline of this presentation is about image matching and then types of image matching techniques. Then I will talk about least square matching and the challenges in image matching. Then improving the image matching speed. Motivation. Actual image matching is considered as the main task in photogrammetry and computer vision. It's considered as the active research area because in case if we found the corresponding point or we match the two pixels successfully, we will able to use the coordinate equation to find 3D object coordinate or 3D point which is consists from x, y, z. By finding the x, y, z or object coordinate for the whole point on the image, on the stereo image, we will able to produce a 3D model for the area, which is considered as the main ingredient or main component in digital city urban planning as shown here, and developing of smart cities and ground modeling or digital surface modeling and other. Let's talk about image matching and what does it mean. Image matching is the process of establishment of the correspondence between each pair of visible homologous image points on a given pair of the images. As you can see here, this is a studio image taken from two different locations for the same area. As you can see here, we have identified a point on the left image and we are trying to find the corresponding point on the right image. First of all, we will uh, uh, put a window around the point because it's difficult to compare specific pixels with each other. Therefore, we will fit a window or we will put a window around it, let's say 7 by 7 or 9 by 9. As much as we increase the window, it will give us a better result, but that will cost a lot of time. What we will do, we will search around the area in the right image, and at each step we will measure the similarity. As much as we were able to find the similarity, the maximum similarity will mean the corresponding point. It means on that point. Let's talk about the image matching techniques. Actually, it's divided into three areas: intensity-based or area-based matching, feature-based, and relational. Intensity-based is comparing the intensity value. It goes from absolute difference, square difference, normalized cross-correlation, least square matching, semi-global matching, and dynamic programming. Regarding the feature-based, it's comes from relaxation, dynamic programming, robust estimation, cross-correlation, and graph matching. Regarding relational, it uses geometric or other relation between feature and structures, combination of the features, corresponding established by tree search technique. Let's talk about least square matching. Least square is highly a nonlinear process and therefore requires a very good approximation value. Actually, it provide a subpixel accuracy. In extreme case, it's about 1 over 10 pixel, and even better, some references gives about 1 over 20 pixels. It's area-based algorithm uses the horizontal normalized intensity values to estimate the disparity for the center pixel of a template window. Actually, the main shortage in this method is require relatively accurate initial values, about 1 or 2 pixel errors. Far from the object, the least square transform the template window of one image to other by a factor transformation. As you can see here, in this window we have a cross and we want to match with this one. What's doing actually fixing this one and rotating and shifting this window. As you can see here, it will rotate this window in order to match this window. This is the original and this is search window. This is the sample grid on the rotated surface. In this case, as you can see here, we have a window. If we compare these two windows, it will fail because for example, the black part is around more than quarter. but here it's less than quarter, therefore it fails. But in least square, it will rotate this window in order to fit the geometric distortion of the area and then compare it successfully with the source window. Let's derive the model of the least square model. First of all, we have a template, this one, and we have a page or search window. What we will do, we will modify based on the affine transformation or shift or rotate the window or skew the window until it will give the minimum error. Let's mark the template, for example, the fixed window with F and the search with G prime. And the error is what we will make, we will minimize or normalize with this square, and we find the minimum values. Okay, we will change or we will shift this window until this value will be minimum. In that case, it will give us the corresponding point. The radiometric changes, and due to the radiometric and brightness value, we will add this one in order because maybe there's a difference in the radiometric and contrast value. What we will do, we will substitute this one with this equation, and it will give us R naught 1 plus R1. This is for radiometric and contrast value in order to adjust the both template and search window. And G2 is for the affine transformation. This Gx2 Y2 is represented as you can see here. We will modify these values in order to be fitted based on the affine transformation. Then following the least square system obtained by substituting the transformed function, we will get this value. As you can see here, fx1 e1 plus ex plus the error equal to the right side or search side. This is for radiometric and brightness, and these are the window. By substituting these two values x2 y2 here, we will get a window or set of the parameter, which consists from 8 parameters, 6 for affine transformation and 2 for radiometric and brightness value. The fxy equal to g naught x naught y naught, and as you can see here, we will substitute or linearize the equation because the nonlinear is difficult to be solved. With this square, we will use the linearized by Taylor series, and we will get this value. The gx and gy is represented by the differential, partial differential around x and y, and the dA1 and dA2, dA3, dB1, dB2, dB3 are the affine transformation delta value. And each step we will try to find the delta of affine transformation. Actually, the least square method, as you can see here, we will be represented as a vector. This is the x prime, and this is the value of affine, and this is the radiometric and intense or contrast values. And these are the A matrix for representing the values of the derivative in the x and y value. And the least square solution for L, we will represent the difference between first pixel on the left image and the right, and the first pixel on the right or search window. This will give us the by representing the above equation in the least square, we will get here, as you can see here, this L plus the residual equal to A times x value, and x prime or the affine transformation and radiometric intensity and contrast value will be obtained by this equation. Let's solve the least square application. First of all, we will identify a point, for example, this point here, We will identify by on the left image by using row and right or row and column for the left, and we will find approximate value for this one. Let's say on the right image, okay, this one by 922 by 245. By using the, for example, C++ software or C++ code, writing code, we will initialize a value uh, for the values of the affine transformation, and for example, for the R1 and R2 radiometric and uh, intensity and contrast value. By running, we will get this value after 9 iteration for the point on the left image, which is 92 by 218. We will get this value 91 by 245.596. As you can see here, the corresponding point has been successfully identified, and the variance or the quality of the error is 0.02, which is low, which means the result is the result. Let's talk about the image matching challenges. There are many challenges on image matching based on Zhang 2005. Actually, the image matching will fail when there is no texture or very poor texture like a snow or like a wood. It will be very difficult to compare two pixel values, and therefore it will fail. Or occlusion or distinct object discontinuity. As you can see here, for example, when the plane is here, this part is occluded while this part is appear. But on the right image, this one will appear and the other part occluded. Therefore, this part will fail in order to find the corresponding one, because when we identify pixel here, it will not be possible to find the corresponding point on the right side. Therefore, it will fail. Local object patch is no planar face insufficient approximation. Actually, the local object or the stop that will be difficult to match. Repetitive structure, as you can see here, if we identify a point, it will be there are many similar points, therefore it will fail to find a corresponding point, or there's probability or high probability to get wrong point. The shadow or moving object will cause the image match to fail. Multi-layered and transparent objects, which will also lead because of low reflectance or reflectance, will be difficult to find the corresponding point. And radiometric artifacts like specular reflectance and other, for example, this one, especially in satellite image, there will be artifacts in the image, therefore it will not be possible to match with the other image. In order to speed up the image matching, a template is specified to be very costly competition. It's possible to reduce the competition time by following the below steps. Use rectified image or make a search along 1D instead of 2D. This is will be done by using photogrammetry. Use more than 2 images will also speed up the operation. A limit of the search space for the corresponding point. Instead of searching the whole image, what we will do, we will search just a limited area. A prior modeling of the object point. For example, a prior location. Hierarchical cost to find strategies also limit the search area. Best first strategy using features sequentially. These are all the most algorithm methods or methods that can be followed in order to minimize the search area. Thank you very much for your listening, and I hope that you will get benefit from this lecture. Thanks a lot, and have a good time.